for joining us. We should be starting in a few minutes. And welcome to everyone who's joining us via our YouTube channel. Remember, you can also watch our talks on YouTube Live via youtube.com/SpaceStoreLive. And tonight we've actually got Michael Curtis-Rouse in, and we're going to be talking about building better rockets. Can't wait for this one, actually. A big fan of rockets myself. As I'm sure many of the audience are. Also, a reminder to everyone here is we actually have our second ephemeris quiz night tomorrow. And we're twisting things up a little bit. So please remember to register for that, because it's only going to be on Zoom tomorrow night at 5:30 p.m. You can register via our website or any of our social media pages. You'll find a link to register. You can join in by yourself, or you can join in with your family and come and test your knowledge, come and test your space knowledge, I should say, for a bit of friendly competition. And yeah, a warm welcome to everyone else who's joining us now. Thanks for joining us at Space Store Live Thursday Night Talks. And a warm welcome to everyone joining us on YouTube. We are running a couple of minutes late tonight, but I do apologize for that. But sit tight, and we should get going in a few minutes. And for those of you who are new to Space Store Live, you might have seen on our YouTube channel, we have Kids AM back up and running every week, where we do some amazing hands-on kids activities, all space themed. So please do go check those out when you get a chance. And next Tuesday, we should also be welcoming back Terry and Nick for their fortnightly roundup of space news. So that's all the latest and greatest space news brought to you by Nick and Terry, who are avid astronomers and both have worked in the space industry. So do go check them out. Hi, Anna. Hope you're well. Thank you for joining us. And there we go. I think Mike's in the house. Just going to unmute you, Mike. Oh, there we go.
Hi, are you good for me to switch?
Hi, Mike. How are you?
Very well, thank you.
Awesome. Thank you so much for joining us on Space Store Live.
My pleasure. Always good to join an exciting group of individuals and talk about stuff we all like to talk about.
Awesome. So for the audience who's joining us now, do you want to give them a little bit of an insight as to what we're going to be talking about? What you're going to be talking about?
Yeah, absolutely. So I'm going to be talking basically about how we build better rockets. It's hard to imagine that you need better rockets when we have so many different rockets active. But the reality is that we need to build rockets more efficiently, we need to build them faster, and we need more of them. So I'm going to be taking you for a journey basically of what makes a good rocket, how rockets are built, what technologies we're using to build better rockets, and where that journey is going to take us.
Awesome. Yeah, I think everyone's really, really excited. Just one little thing is we've got a few messages coming in from the audience saying we can't hear you properly.
Okay.
It might be your input volume or speaker.
Okay, can you clarify if that's any better?
That is amazing.
Okay, good. All right, let's run with that then. And you good for me to switch to my presentation?
Yes, please, if you want to switch to your presentation. And then just a reminder to everyone is that please feel free to throw in questions via the Q&A or the chat whilst Mike is talking. And then towards the end of the talk, maybe around 5:45, we'll try and do a Q&A.
Sure, great. Thank
Awesome.
Lakshya.
Awesome. I'm going to go off now and I'll come back around 5:45.
Great, thank you.
Brilliant.
Great. Good evening to everyone on this call. My name is Mike Curtis-Rouse. I'm the head of manufacturing for space at the Satellite Applications Catapult. I'm also the chief experience officer for Space Store, and I run my own external consultancy around space as well. So I'm going to talk about basically why hot rockets are good rockets. And the image actually in front of you is actually a rocket engine, though it's potentially a rocket engine that, unlike anything you may have seen before, this is what we would call an aerospike. And it's a completely different type of engine, not one which actually thus to date has actually been operated in space, but one which offers enormous potential in terms of being more efficient, being easier to control, and ultimately being easy to manufacture. So it's worth looking at why are we talking about rocket engines? Why are we talking about the need to build better rockets? Well, right now, globally, there are a phenomenal number of companies trying to build rockets and various types of launch vehicles. 10 years ago, that wasn't the case. 10 years ago, there were about 10 companies. Today, we have 246 launch vehicle companies around the world trying to build rockets, space planes, and other types of means of getting into space. Many of those companies aren't really going to probably survive in the long term, because the reality is that they're operating more on exciting PowerPoint decks, and their science and their engineering is not well founded, but some of them will. And one of the exciting aspects is that within the UK, we've got over 16 companies of various sizes trying to build rockets, space planes, and other flavors of launch vehicles. So there's a real appetite out there to build new types of ways to get to space. So this is fundamentally rocket science, and people, the expression that if you're smart, you're a rocket scientist. Well, actually, rocket science is pretty simple, and the maths in front of you, some of you may be looking at this and thinking this is absolutely horrible, and some of you looking at this may thinking, you know what, actually this doesn't look that complicated. And the reality is it's not. Rocket science isn't complex. Rocket science is basically you lift something fast enough and high enough with enough velocity, i.e. how fast it's moving in a certain direction, away from the Earth to negate the effects of gravity. And if that happens, you're moving more than typically about 7.5 kilometers a second, then you end up in orbit. Now, the key thing about being in orbit is you still have to keep on basically having that thrust, because if you don't, eventually gravity will grab you and pull you back to Earth, either disastrously in the cases of big objects or less disastrously in small objects. Most of you have probably seen a shooting star at some point. Most of the time that's meteorites or meteors basically entering the Earth's atmosphere and burning up. Occasionally it's part of a small spacecraft or a satellite or something like that. And for the most part, when they burn up, it has a negligible effect on anyone else on Earth. Big things, though, if they re-enter, can have a very negative effect. So it's important to stay up there. So just in terms of context, I always think it's interesting to think about where space is in reality, because space isn't actually fundamentally far. The reality is that between Oxford and space, where we're going to look straight up, we're talking a distance of about 400 kilometers. However, if we're talking about the actual edge of the atmosphere where we define space, what we call the Kármán line, which is about 100 kilometers away, actually in that distance, it's no more than the distance between Oxford and London. Actually, it's slightly less. So actually, in reality, it's not that far. Now, if you drive to London, and assuming you can get through the traffic, it probably takes you about an hour and a quarter to get into London. Reality is, if we launch a rocket, getting it up to 100 kilometers literally takes 30 seconds to a minute or so. It's not particularly slow, but you have to be moving that fast, as I said, because otherwise you would just fall back to Earth. But when you look at rockets, again, they are basically pretty simple. You need a fuel, you need an oxidizer, you combine them together, you add a spark, you get a bang, and you basically get a whole series of gases which kick out the rear end and move something forward. And the difference between the water rocket on the left-hand side and the Ariane rocket on the right-hand side is just basically size. The water rocket isn't going to go more than probably 50 to 100 meters. The Ariane 5 rocket on the other side is comfortably going to a couple of thousand, but it's just about size and scale. but it is hard to build rockets, and it's hard to build them reliably. The left-hand image is some of the ill-fated early Falcon 9 SpaceX landings, which, to be fair, that's not necessarily the fault of the rocket per se, but trying to land the rocket on a barge at sea in one piece is pretty challenging, and you can see the disastrous results of when it actually does fall over. And the other images on the right-hand side is model rockets. Well, I certainly wouldn't want to be chased by a model rocket, but they can be unpredictable. I think that chap got away with it. And in the lower right-hand corner is the Japanese H5 launch vehicle, which failed a couple of years ago on takeoff. And this all comes down ultimately to rocket engines, fuel tanks, and the various gubbins which go inside them. One interesting thing, though, is people always assume that rockets are expensive because of the fuel. And the reality is rockets aren't expensive because of the fuel. Rockets are expensive because of the engines. The engines make up the cost. Now, while the fuel costs are typically for a two-stage rocket, so if you pick, say, Falcon 9 comparatively or something similar, the fuel costs are less than 1%. They're tiny. But the fuel actually makes up 90% of the mass of the second stage and 95% of the mass of the first stage. What drives the main cost is the engine and the airframe for the first stage. The engine being more than 50% of the actual cost of the first stage, the structure a fractional 25% or so, and everything else, avionics, electronics, valves, actuators, etc., falling into the remaining percentage. And on the second stage, the engine and the avionics, it's a smaller factor this time, but the effectively the second stage still takes up about 25%. So the costs of the launch vehicle, you can basically say that 60% of the cost of the launch vehicle, slightly more, 65% perhaps, is actually down to the cost of the engines. So if you can make better engines, more efficient engines and higher performance engines, and you can make them more cost effective, you lower the cost of getting things into space. And then that fundamentally directly translates into the cost that you ultimately, a launch provider charges someone to put a satellite, a person, a project, a space station into space, because it all comes down to cost per kilo. And today the costs per kilo are dropping below $20,000 a kilo. 10 years ago, they were more like $30,000 a kilo. The aspiration is to get it down to as low as $1,000 a kilo. And you can fairly rapidly do the maths that if you weigh, for example, 75 kilos, then the equivalent cost of getting a human into space is about $75,000. Now, that's a pretty far off concept. The cost of getting astronauts, certainly using SpaceX's new Crew Dragon to a space station, is still in the region of $45 to $50 million per seat. Now, that's half the cost that Russia was more or less charging for Soyuz, but it's still a phenomenal cost. So we've got a long way to go before you're being able to basically go online with your travel agent and book a seat to go to the space station. These rockets basically represent pretty much the state of the art. On the left-hand side, you have the Vulcan engine made by Safran Industries in France, built for the Ariane 5 European Space Agency launch vehicle. These rockets are big. I don't have a person comparatively in scale there, but the Vulcan engine there is comfortably 3.5 meters high. The engine next over, the RS-25, currently, well, was used for the shuttle for its main engines, and is now being reinvented to be utilized for the Space Launch System, which is NASA's replacement for the shuttle. That engine is comfortably 4 meters high, weighs several tons, hugely complex. SpaceX's Merlin engine, still a couple of meters high. You can see there's an evolution. Things are getting perhaps more slim, more ergonomic in design, almost slightly sort of biologically inspired with some of the structures, but it still basically looks like a big bell housing. And finally, over on the right-hand side is the Rutherford engine from Rocket Lab, another new entry to the launch vehicles, building, in this case, it's almost fully a 3D printed, additively manufactured engine. And in the case of that engine, instead of having pumps which provide the fuels, which are usually powered by gases, which are combusting inside the engine, the Rutherford engine uses electric motors. It makes it more compact, but it also means you have to carry bigger batteries on board your spacecraft. And the risk which goes with that, if things go wrong with your batteries can explode when they get hot. Many of you will probably be familiar with the concept of a battery short-circuiting. If a battery gets hot and short circuits on a spacecraft, on a launch vehicle, you can lose your entire launch vehicle. So there are swings and roundabouts depending on which technology you look at. Now, when we're still looking about ingredients of things, there are some good ingredients which are worth having. And all the images here have the commonalities there. So the Falcon 1 rocket towards the bottom end, the concept for a new version of Concorde, or effectively a super hypersonic aircraft operating from the UK, Sabre, which is one of the products from reaction engines based over in Abingdon, the Merlin engine in the middle being suspended, and even on the far right hand side, the Apollo command module. All of these engines have something in common, and that's basically the material. And in this case, it's a material which allows you to operate engines at high temperatures but run very cold propellants to fuel through them. And it's something which is basically, we call it cryogenic resilient. It's resistant to low temperatures, but it can burn up. It can deal with high temperatures at the same time. It's a weird material, but usually we look for these materials and we call them refractory metals. You might have heard of some of them. Tungsten, for example, is used in a whole variety of applications, more commonly originally in light bulbs, now used all over the place, from X-ray detectors to security scanners. And materials like tantalum, which is used for medical implants, and niobium, which is used to make magnets. These are refractory metals, high temperature metals, which compared to the other elements in the periodic table, can make alloys which operate at very, very high temperatures and give properties which are hugely desirable from a rocket engine perspective. Now, as I said, engines get hot, but you want to run them cool at the same time. A cool engine is a happy engine, but the hotter the better. Now, that sounds like a contradiction. Most engines, with a few exceptions, basically work with the fact that you run a cryogenic propellant, often usually the oxidizer, usually liquid oxygen. You run around the jacket of the engine, and that basically goes around the jacket before it goes into the engine to be burnt. And what that does is it cools the engine down, which means that you can run the engine at a higher temperature technically than the metal could withstand. And at the same time, the heat that the coolant absorbs from the engine increases the energy of the propellant going into the engine. So conversely, even though you're technically cooling the engine, you're actually putting more energy into the engine at the same time. If any of you are familiar in terms of how jet engines work, you'll know that jet engines on modern aircraft today basically run at a temperature higher than the material than the actual jet engines are made of. So jet engines actually cool themselves down by the chemistry and the mechanics of the way they operate. So when you look next time you're flying, and assuming you're not nervous flying, when you look across at that gas turbine engine, which is basically running under the wing, think about the fact that technically the temperatures in it exceed the melting point of the metals which are used to make that engine. The reality is of course, it doesn't melt, and aircraft engines are phenomenally reliable. They spend more time in the air than they do on the ground. They spend more time running than they do not running. But the reality is they've been built in such a way that you can run them at a higher temperature than the actual melting point of the materials used to construct them. And it's exactly the same with rocket engines. We want them to run cool, but we want them to run hotter because that burns more propellant, which gives us a higher energy out and a cleaner efficiency in terms of combustion. One of the other problems, of course, is with rocket engines which run hot, is that if they run hot but not hot enough, if you're running a propellant, for example, like kerosene, which is basically petrol in conventional senses, but used more for aircraft. Kerosene basically is relatively dirty. It generates a large quantity of carbon. If you burn it inefficiently, that carbon builds up in the inner walls inside a rocket engine and causes what we basically relate to as hotspots. And those hotspots basically is where carbon is building up. And it's a little bit like the carbon you would see inside a chimney, for example, or if you ever run your finger around the inside of an exhaust pipe on a car, it will come away with effectively that soot. That soot is bad for rocket engines because what happens is you end up with an inconsistent heating pattern inside the engine. And that basically means that eventually you'll get the heat will burn through the cooling jacket of the engine. Now, if you can imagine, of course, you're putting hot rocket fuel down through the middle, which is combustioning and exiting the far end. And then you have a hole in the side where your oxidizer, liquid oxygen, is basically cooling the engine. You basically get a flare. And this is one of the ways that rocket engines very rapidly, as we say in the aerospace industry, unintentionally dismantle themselves. And if a rocket engine unintentionally dismantles itself while you're running it, you better hope you're a long way away because there's no going back. That whole launch vehicle will very rapidly take itself apart in a fairly spectacular explosion. So if we want to do things better, we need to basically look at new materials, etc. And while the image on the bottom left-hand corner actually looks like it's been made out of clay, that's a type of tungsten which has been deposited using a type of 3D printing. And it's actually quite akin to knitting, really. It's basically where you extrude more or less a filament of hot metal, and you basically layer it round and round and round and round. It's so hot, it basically bonds together. Now, the general fidelity, the detail of that is not great. You would have to do quite a lot of machining, but it does allow you to bring together different materials. And the image on the right-hand side is a microscopic analysis of two different materials, copper and Inconel, which is an alloy. And basically, those, you can see that interface, the bottom edge is the copper-like material, the upper side is the Inconel, but actually we would consider that a very good bond. I mean, that's a significant magnification. But the two materials are basically blended together, and that allows us to create effectively alloys which are suitable for high temperature energy components and still benefit from the practicalities of both how we manufacture them, but the ability to machine copper. Copper pipes, I'm sure many of you have touched or potentially used to make things in the past. Copper's malleable. It's easy to bend. If you have a copper pipe for a heating pipe, you can very comfortably, you don't need to have a lot of strength, you can bend it in your hands into a curve. If you try to do the same with the Inconel pipe, nothing's going to happen. You'd need to have the strength of the Incredible Hulk to bend Inconel. It's a phenomenally hard material. But by bringing those two materials together, copper, which is a hugely thermally efficient material, incredibly good at heat transfer, and also electrically conductive, which can be useful. Inconel, which is highly resilient to cryogenic temperatures and very high temperatures, whereas copper is not. You can bring those together to create a complex engine where you're levering the properties of one material against the properties of another material. So this really comes back down to basically better DNA. Better DNA makes better rockets. So the engine on the left-hand side, this is another SpaceX engine. So this is a nozzle for a Merlin engine. Effectively nozzle is made out of a material called C103. It's what we call a niobium alloy. It's a niobium, to go into the detail, it's a niobium hafnium titanium alloy, and it's high performance and heat resistant up to just below 2400 degrees Celsius. It's also incredibly resilient as well at the same time to cryogenic temperatures, and it's reasonably easy to work, reasonably easy to machine. So that actually becomes hugely effective when you're taking materials like that rather than using, for example, a titanium or an aluminium, which couldn't, one of them could withstand the temperatures, but one of them couldn't give you the structural strength you need. Or if you went with Inconel, the weight would be so much that the rocket engine would lose its overall performance. So you're specifically selecting materials. The images on the bottom right-hand corner are rhenium, another metal, which has some very high temperature properties. And these rhenium chambers are basically being made by literally chemical deposition. Electrolysis would be another approach to doing it, but basically where you're building something up layer by layer by depositing a material in a vapor. It takes a very, very long time, but you can build very high temperature structures up. The drawback of it is rhenium is phenomenally expensive, and it takes a very long time. So those little structures there are actually only a few tens of centimeters long. They're great for certain applications, in this case, a defense application. But if you wanted to build something like the rocket engine shroud on the left-hand side, it would take you probably years to manufacture something of that size. And the cost would be running into comfortably the hundreds of millions, if not more. It's worth touching on some alternative types of fuel as well, because people are playing with how do we make better fuels. Now, this is a company based in the US, father and daughter, new space startup. I cannot remember for the life of me what ANS stand for, but something ANS space. And they've been basically, you can see those are weather balloons with a rocket hanging on the underside. This is what we call a raccoon. It's a combination of a balloon and a rocket. Kind of crazy, you might think, and generally most of us do think it's pretty crazy. And what you do is basically you use these balloons to lift this rocket up to about 30 or 40 kilometers. And then at that height, you drop it, release it from beneath the balloons. The rocket ignites and it goes up higher. This is a way of perceiving of getting things cheaper into space. Those of us in the rocket community are dubious that actually if there's any real benefit. The interesting thing about this company, though, is that they are 3D printing their fuel. So some of you have come across, have probably used 3D printers, may have seen them in a university or school setting or on the internet, etc. And you can see the image on the right-hand side. It's very, you can actually almost see the filaments on the right-hand side. This is 3D printed with a 3D printer you can buy on the internet for a few £100s. And it's basically a type of ABS, type of plastic. And it basically burns and it gives you a relatively high thrust. So it's quite an interesting way of doing things. Not particularly conventional and certainly not good for getting satellites or humans into space, but for putting small payloads, it may well have some merit. The other type of propulsion, and it's just worth mentioning, is, and it's fascinating, something called electric propulsion. Now, chemical propulsion is great, gives you a high thrust. It's easy to get you off the Earth's surface into orbit quickly and efficiently. However, it's expensive, it's cumbersome, and you can't really turn it off. You can use chemical propulsion for moving satellites around an orbit for stabilization control or moving them higher up. So, for example, the International Space Station, which sits at an orbit altitude of 400 kilometers, constantly has to raise itself using chemical propulsion motors to lift itself higher to stop it basically falling back to the Earth. Increasingly, we're moving satellites into orbit, but to a lower orbit. They go up with rideshare with a series of other satellites. They go up to a point, and then they get released. And then they would use something like electric propulsion. And this is a Hall effect ion drive on the left-hand side. And this is basically by basically superheating a rare gas like xenon or neon or krypton to the point that you excite the gaseous ions and you basically accelerate them down a magnetic tunnel. And as they exit, while their actual thrust comparatively is tiny, over a period of time, you actually build up not an insignificant amount of thrust. And you can do this with a huge degree of fidelity, relatively low cost. It takes a much longer time to get to an orbit, say, of 10,000 kilometers from 400 kilometers, but it's much cheaper and it's much more efficient. And one of the major advantages of it is that a little xenon gas combined with electrical power, because this is the driving effect, which you can harness from solar panels, goes a very long way. Unlike chemical propulsion is, once you've used it, it's basically gone. It's very energetic, it gives you a big boost, but once you've used it up, that's it. Now, of course, electric propulsion engines also run out of their rare gases, but they do it over a much slower time. The engine on the left-hand side comparatively is about 20 centimeters in diameter. It's not huge, but it can be highly efficient. And this is being increasingly mulled over for the use for interplanetary transfer, moving between the Earth and the Moon, or potentially the Moon and Mars. So state of the art does mean advanced manufacturing, and all the engines I showed you earlier from SpaceX and Rocket Lab, they're all basically built with additive manufacturing, 3D printing. And here you can see some of the images. So NASA have also created a new 3D printed engine they call Vulcan 1, nothing to do with the Ariane 5 engine, but going along the same lines. The Merlin engine, bottom left-hand corner, is heavily 3D printed, and the engines on the right-hand side are being manufactured for a company called Launcher. These engines are being built in the UK, literally just down the road from here in Newbury. And you can see when I was talking about basically that cooling channel, you can see that porous structure in that inner skin. That is basically, that is the coolant jacket. So you're pushing the fuel through that matrix of material to cool the engine down. So 3D printing is fundamentally a really critical technology for building engines. The drawback with it is it's limited to the size of the engine, and it's phenomenally expensive, and it requires a high degree of skill. Coming to the end of my presentation, but I just thought it would be worth sharing with you some of the reasons why we want to build more rockets, etc. So this is a map of the UK. This is a slide from Launch UK, which is part of the UK Space Agency's working group. These are the future spaceports in the UK, which are either being proposed or being constructed. In Scotland, you can see there are basically 3 vertical launch spaceports in the Western Isles, in the Shetlands, and in Sutherland, which is at the tip of the Scottish Peninsula. These are all vertical launch sites where companies like Orbex, for example, and Skyro are planning to operate out of. And then you have other sites for horizontal takeoff for spaceplane-like activities in Campbelltown, Prestwick, Snowdonia, and Newquay. Newquay most recently talking about, and Virgin Orbit talking about operating their air-launched rocket system, the one which actually launched out of California a couple of weeks ago and exploded after 9 seconds. But they're expecting to be able to do their first test flight later this summer from Newquay, lifting commercial satellites. And they have a contract with the Royal Air Force to do so. And finally, so these are some of the launch vehicles being built in the UK. Now, Virgin Orbit, top right, isn't actually being built in the UK. I mean, technically it's Virgin Orbit UK, but they're based in California with their headquarters in Los Angeles. So I wouldn't say that's particularly UK-esque other than being Virgin. Top left is Skyro. They are a Ukrainian-Scottish launch company. They did one of the first test fires of their engines a few weeks ago, of a 30 kilonewton engine in Scotland. And they are expecting to be launching rockets probably sometime in the summer of next year. Bottom left-hand side is Orbex, who are based in Denmark and also in Scotland. They're expecting to be operating early next year from Scotland as well. That's very much a very UK-based rocket. Almost all the technology developed in the UK or working in partnership with some of the companies in Denmark. And finally, on the right-hand side is Firefly, who probably will be operating out of Scotland under the guise of Lockheed, who will be providing one of the launch capabilities on behalf of the UK Space Agency to put satellites into space. That's my last slide. My email address is there if you would like to contact me regarding it, anything I've spoken about so far. But otherwise, I'm very happy at this point to take questions. Thank you.
Awesome. Thank you so much, Mike, for such an incredible talk.
My pleasure. As I said, always good to talk about what we enjoy and what we do. Definitely.
I see we have a few questions coming in on YouTube. Just a reminder to everyone on Zoom to make sure you send them in through the chat or the Q&A. We're going to be here for around 15 minutes more trying to answer your questions. I actually had a question. Just thinking about the rockets was, I'm sure thousands and thousands of people who are even vaguely interested in space would have watched the Demo 2 launch a couple of weeks ago, with NASA SpaceX launching Bob and Doug to the International Space Station. Of course, that was a ground launch, whereas the Virgin Orbit test was a carrier spacecraft. What's kind of the key differences between the two types of launches?
Well, the reality is that air launch means that you can't actually lift as much to space. So you're basically using a carrier aircraft to climb up to, say, 20 or 25 kilometers, from which point you are then dropping a rocket which is underslung under the wing. It's technically perceived as cheaper, more efficient, and fundamentally safer because you're dispensing with the first stage of the launch vehicle and you're only having one stage to the rocket. However, the drawback is you can only lift so much mass. So while it's a cheaper process, it does mean that you can only launch typically smaller spacecraft, but it is also more responsive. So Virgin Orbit technically can operate anywhere in the world. There is a runway they can take off, and they don't need a particularly long runway. A couple of kilometers is more than sufficient. And they can be more responsive as well, which is one of the reasons they have a contract with the Royal Air Force for launching responsive payloads. So if we want to put a responsive satellite for communications up in support of UK forces, we can very rapidly do that. And we don't have to worry about the weather or anything like that, because vertical spaceports basically are highly weather dependent. So one of the challenges about Scottish spaceports is, while they are in potentially interesting locations, the risk is the weather may only be appropriate perhaps for 50 or 60 days of the year. And that in itself is more than a little challenging.
Yeah. So would you say kind of the carrier aircraft type of rocket launch would be more suitable in the coming years for smaller satellites?
You're never going to see carrier aircraft lifting big rockets. They're only ever going to be small rockets. So you're never going to be lifting more than probably payloads of perhaps 400 kilos or thereabouts to orbit. It just simply doesn't scale. You can't attach a very large rocket clearly to the underside of an aircraft. And if you did, the economics of it would start to decrease compared to that of vertical launch.
Just a question coming in. So anonymous attendees asking, how are the planes adapted to carry the rockets?
Well, the Virgin Orbit 747 is, to be honest, it's been stripped out, so it's got slightly more powerful engines, so it can climb and fly higher. The inside is being stripped out because they also bring their launch vehicles from the manufacturing facility in California to wherever they're launching, so they can carry up to 2 launch vehicles in the belly of the aircraft. And then they have their command and operations center on board as well. So it's a very effectively integral operation. Externally, comparatively little. Basically, the engine is hanging from a pair of pylons off one of the wings from a supporting perspective. Now you're going to do a comparative balancing exercise to ensure that that mass on that wing doesn't upset the balance of the aircraft. But in reality, relatively little.
That answers your question. Another question: what might we see in the future for powering rockets? Anything left we might laugh? Oh, sorry, that's just a slightly confusing question. What might we see in the future for powering rockets?
Realistically, there's very little in terms of you can do anything different, because it comes down to basic laws of physics and energy. you need highly energetic fuels to lift things. So you need fuels. We're seeing beginning. Some companies are looking at greener fuels, as they term it. So they're making fuels from recycled plastics and things like that. But you're basically still going to need liquid oxygen, and you're going to still need a propellant, a fuel which has a high energy value. So there may well be some flexibility there, but we're looking at gases like propane and methane being extensively used. Orbex are planning to use propane, and Skyro are using a recycled type of plastic. But that's about as exciting as it gets. There is basically, unless you talk to someone like Spin Launch, who are using a giant catapult, whether that will work or not, to launch things into space in California, that's great for static objects, but it's not great for objects which are have people on board.
How does the catapult one work?
Nobody knows. It's highly confidential.
Okay. Someone suggesting quantum power.
I'm not sure what that means.
QVT?
Again, without knowing what, there were so many acronyms, I have no, if they can break down what that acronym means, I might be able to say, but beyond that, I don't think I can comment.
So it's a quantum vacuum thruster.
Oh, okay. So I think, yes, this is the concept of moving energy backwards and forwards. NASA had a study into it, etc. It's been proven foundless thus far. I mean, it's possible we might see new forms of physics which allow us to do something, but we're not going to see anything exciting like that, certainly for the next, I would suspect, a few decades.
Nafisa's asking, which UK spaceport will have the first launch of a satellite?
I'd anticipate probably Newquay will probably have the first horizontal launch. For a vertical launch perspective, it's hard to tell, but I suspect it will probably be Shetland, and that may be Orbex. It might be Sutherland, but it's going to come down to a larger, not so much spaceport readiness, but the UK Space Agency having readiness in terms of the licensing and the regulation needed.
Yeah, I hope that answers your question, Nafisa. A question coming in from Chris, and he's talking about, of course, the environmental impact on how much kind of the carbon footprint of launching a rocket, and how does that compare with day-to-day airline carriers?
No, it's pretty huge. Absolutely, it's pretty huge, but there's no getting away from it. So as I was talking in a presentation this morning, at the end of the day, if we want to try and reduce our carbon footprint on the planet, and we want to be able to get a good idea of how the planet is doing, we're going to need a barometer to do so. And we can't do that just by monitoring from the terrestrial side. We have to be able to launch things into space. And our entire society is heavily dependent on telecommunications, navigation, etc. I suspect there are many people who have no idea how to navigate without the use of Google Maps now. So yes, we could stop doing that, but we won't know actually how much we've improved the planet in terms of pollution control, etc. Nor will we be able to get anywhere, nor will we be able to talk to anyone. So we can reduce the amount of activity we do in space, but we'll be very rapidly moving back to pre-medieval Europe.
Definitely, I think it's a good argument right there as to why we need to continue launching satellites.
Certainly, one of the interesting things about COVID, for example, has been that increased dependency on telecommunications from working from home. So we're only going to see that grow. On the flip side, we've seen people travel less, so there's actually a benefit there in it, as well. Comparatively, rockets predominantly kick out the more carbon dioxide, nitrous oxide, and water vapor more than anything. The chemicals they use are not actually that unenvironmentally friendly, but they aren't great for the environment at the same time.
Yeah. Rana Johnston's actually raised an interesting point, and I remember at your Space Store talk a few months ago, pre-COVID, we mentioned this topic, and the topic is space elevators. So Rona's asking, is there anyone looking at space elevators, or are they never going to work?
They work perfectly well. We just don't have the materials to make them. So the principles are completely sound, but we need a material which has an exceptionally high ultimate tensile strength in the order of megapascals. And while there are materials like carbon nanotubes which exist, we can't manufacture them in high enough volumes or integrate them into effectively the cables we need to make to support such a structure. Because even though that cable is only potentially a few tens of centimeters in diameter, it would need to be 36,000 kilometers long. So the equivalent weight of it would be running into the tens of thousands of tons. And we don't have anything like that as a material which we can utilize today, which would give us that mechanical strength.
Yeah. I mean, for the audience who don't know what a space elevator is, can you describe what it is?
It's literally pretty much as you just described it. It's an elevator where you anchor a rock in geostationary orbit, so it's always overlooking the same point of the Earth at any one point, and you attach a cable to it, and you basically run an elevator up and down it, and it's kind of the holy grail of getting things cheaply into space. You might be able to do it on a planet where the gravity pull is lower, so Mars might be more viable, or Venus, but you have to get there first to do it.
Yeah, awesome. I've always been fascinated by the concept of having a space elevator since childhood. Just a reminder, please do send in your questions. We're going to be here for a few more minutes with Mike talking about rockets. Just a quick whiz over to YouTube to see if there's any questions on YouTube. Please do carry on sending your questions through. So I mean, there's no questions currently, but please do send them through. I just wanted to get a bit more knowledge, insight into what your roles have been in the like rocket industry or satellite industry, if you like, so far. So yeah.
So I've been, as I said, I lead on manufacturing for space for the Catapults. So that's very much focused around the development of our spaceports, launch vehicles, and commercial and technical business cases for the companies operating that space. I've been fortunate to have led activities in terms of planetary robotic field trials in the Utah desert with the UK and European space agencies, evaluating how we would control robots on Mars and on other planets. And outside of that, my main expertise is in advanced manufacturing, so developing materials specifically for rocket engines. So I've worked with companies like SpaceX and others to develop some of the materials that they use within their actual rocket engines, and working out what the best way to manufacture those materials are, be it with additive manufacturing or be it with other appropriate technologies, some simple and some less so. And in my early career, I worked on electric propulsion for spacecraft, which have now left the Earth and are going into orbit, like D6, for example, around Mercury.
Oh, wow, okay. And then I read in your bio that you actually helped on the Rosetta Mission and CERN as well.
So I started my career working at CERN as a particle, well, I wasn't quite a particle physicist. I was an engineer helping support particle physicists looking for the Higgs boson. So I worked on the Atlas detector. And after that, I worked on what we call field grid arrays, which again are small electric propulsion systems, which were used to get the Rosetta mission into orbit before it started to do its comet survey, etc.
Mm-hmm. Oh, wow, okay. Awesome stuff. I don't think there are any questions from anyone coming in currently. I'm just going to get a final look. Just a reminder, please do send in your questions. But no, I mean, it's been great talking to you about rockets. I've learned so much, as I'm sure the audience has. Oh, not a technical question from Oliver White, but what upcoming space missions launches are you most excited for?
Well, I'm hopeful that ExoMars eventually launches successfully and doesn't explode on launch or subsequently on landing, which is always a risk. And I think, like most people, we're excited to see how the James Webb Space Telescope does when it launches eventually as well. Two very major science missions. But beyond that, I'm excited to see the first UK launch vehicles operate. So when Orbex conduct their first launch in the next 18 months, and the same for Sky Aurora, because that will be really a big moment of inspiration, both for the UK, both for current engineers and those with aspirations to do engineering and do science.
Definitely, yeah. I mean, as Oliver says, he's asking a non-technical question. It doesn't have to be a technical question, just so you guys know. Question on YouTube. Do you know why SpaceX might have appeared so smooth last week? Oh, as Nick mentioned it on our Tuesday night roundups.
Sorry, appeared so what, sorry?
appeared smooth. So the launch of the rocket inside, when they had when they were showing Nick and Doug, Bob and Doug inside the Dragon spacecraft, it appeared really smooth.
A rocket launch isn't actually particularly violent. So they are, and there is a degree of vibration isolation and protection between the launch vehicle and the Crew Dragon module, which sat on the top. But it only looks violent from the outside. Actually, the reality is it's smooth to an extent, but they will be feeling the equivalent of 4.5 to 5 G's worth of vertical thrust, and it would have been, and they would have felt those vibrations, etc. Because you're basically sitting on the top of a very large firework.
Yeah. Well, we don't know why they seem they are smooth. Another question from Nafisa: will we manufacture things in space to bring back to Earth, and what would be the benefits?
So there are certain things we can make in space which we can't make on Earth. Be those pharmaceutics, types of alloys, ultra-spherical ball bearings, new types of plastic, semiconductors and things like that. So we can use the natural conditions of the space environment, the fact that it's very clean, very cold, and there's comparatively little gravity. There's not an absence of gravity, but there's low gravity. So we can make objects, crystalline structures, we can allow metals to cool in a very even and homogeneous way. And the reality of that is we can make products that we can't make on Earth. And subsequently, they may well have terrestrial benefits, so we would bring them back to Earth.
Awesome. Hope that answers your question, Nafisa. What kind of, if there's a specific product that you might be thinking about? I think I've got an intruder. If there's a specific product that that is currently made right now here on Earth, but
space would be one example. So there's a material called Z-Blan, which is a highly efficient, high-performance fiber optic cable, which we can make better on orbit than we can make on Earth, and it's highly efficient in terms of its performance and gives an order of magnitude probably better than anything that we have today. The challenge of it is making it in sufficiently long enough lengths that we can utilize it in a meaningful way.
But then, how does the cost feasibility compare? I mean, you're spending so much to kind of get up to space, and then you're making a product.
The cost of getting into space is comparatively low because it's you need about 1 kilo of raw material to make kilometers worth of the actual material, and the actual material you can sell on Earth for a far higher price than you can of the conventional material.
Right. Okay. Fair enough. I hope that answers your question, Nafisa. I think we are out of questions and almost out of time. Once again, a big thank you, Mike, for joining us. I think we're going to wrap it up there. Once again, thank you to everyone who's joined us on our Thursday night talks. Thank you, Anna, Freddie, Christian, Nafisa, Oliver, Rona, Samuel, Sophie, Chris, Tom. Thank you for joining us. Thank you, Mike. Once again, a reminder, tomorrow night for Ephemeris quiz. Make sure you register for that via Zoom, via our Facebook channel or website. That's going to be happening on 5:30 tomorrow. And thank you so much, Mike.
Thank you very much.
Awesome. I hope you have a great evening. Have a great evening, everyone, and we'll see you tomorrow and then again on next Tuesday for Nick and Terry's Space Roundup.
You too. Stay well.
All right. Bye.